All right, so we're going to start today off with an example because it's going to kind of guide us towards what we are talking about. So I've written down an example problem here. Having misplaced their USB charging cable, an electrical engineering student decides to construct a simple charging circuit using a diode-based voltage regulator as shown below. So here is our circuit. We have 6 diodes connected in series. They should all be forward biased. And since we are assuming VD on is 800 millivolts, 0.8 volts times 6 gives us an approximate output voltage of 4.8, which is well within the range of what can be supplied by a USB cable. USB cables are rated at 5 volts and roughly half an amp. We are also told that if the cell phone draws a constant current of 80 milliamps, we want to determine 3 quantities. The diode current ID, that's going to be pretty straightforward. The reverse saturation current IS, also pretty straightforward. And then the change in V out if V in increases to 9.5 volts. That last bit's going to be where it gives us a little bit of trouble. Okay. So let me see what's popping in chat real quick since there are 3 things. Oh, people saying stuff for attendance. Great. Thank you, guys. Anybody else who's online who has not typed in anything into the chat, please do so now so that I can use that for attendance purposes. All right, so based on the information that we're given, we know that there is a charging current, which I'm going to call IC, of 80 milliamps in that direction. How can I figure out any of the other quantities that I'm interested in? Let's start there. All right. So obviously I'm interested in the diode current, ID, and I would argue that I could find ID if I knew how much current was flowing through my 42 ohm resistor and then used Kirchhoff's current law. Anybody have any problems with that? So this would be another current that we could find. IX, the current leaving our power supply that we're regulating the voltage down to 4.8 volts. So anybody have any ideas on how we might calculate IX? Okay, so what Mr. Posniak is suggesting is that we know the voltage present at the top terminal here of the resistor. It's 9 volts. We know the voltage present at the bottom terminal of the resistor. It's 4.8 volts. So we can simply use Ohm's law to find out how much current is flowing through that. I tend to agree with that sentiment. So we can say IX is equal to 9 volts minus 4.8 volts over 42 ohms is 100 milliamps. Chose that resistor to give us something easy to work with. Anybody have any problems with that level of circuit analysis? So certainly hope not. You guys, juniors, Ohm's law should be pretty straightforward by now. So using this, our diode current, ID, is simply IX minus IC. 100 milliamps minus our charging current of 80 milliamps gives us a diode current of 20 milliamps. So that same current flows through all 6 of these diodes in series. So here is our work for part A. For part B, we know that ID is equal to IS times the exponential of VD divided by VT minus 1. And I'm going to say that this is approximately IS times the exponential of VD over VT. I can make this guess here because VD on is significantly larger than VT, right? 800 millivolts is a whole heck of a lot bigger than 26 millivolts. And so inside this term, the exponential function is going to be significantly larger than that minus 1. So much so that it's not really going to come into play at all. And when we do part C, the approximation here is going to make the math a little bit easier to deal with. All right, so from this, I can see that IS is then going to be 20 milliamps divided by e to the 800 over 26, which I get to be 8.672 times 10 to the minus 16 amperes. So we use good old Kirchhoff's voltage law and Ohm's law to get the answer to part A. We're using our exponential diode model to figure out what IS is. Now we come to the part that's a bit more difficult. We want to figure out the change in V out if V in increases to 9.5 volts. And so I'd like to talk about this a little bit, okay? So our output voltage is set by using the constant voltage drop model for our diode, right? But we know that if I increase this voltage, what's going to happen in my circuit? What's going to happen to the current IX specifically? If I increase the voltage, that current should also increase, right? Which means the current flowing through my diodes should also increase by some commensurate amount. And when we see an increase in our diode current, it stands to reason that we should see an increase in our diode voltage, right? And our output voltage is just 6 diode voltages in series. So if we left this entirely to the constant voltage model, it says no matter how much we increase this guy, the output voltage is going to be exactly 4.8 volts, and that can't possibly be true, okay? So it's going to change by some amount. What we're getting into really is what's called perturbation theory for this nonlinear circuit. So here's how we're going to approach this. I'm going to call this IX1. This is our first guess, okay? So our first guess, and it's a kind of crappy one, but our first guess is the voltage is going to stay exactly the same, and all of that excess current is going to be bled off by the resistor, okay? So that would mean that our first guess says that we'll have 9.5 volts minus 4.8 volts divided by 42 ohms, which would give us 111.905 milliamps. And from this, our first guess at our diode current is just that minus 80, which is 31.905 milliamps. And now that we know what this diode current is, under that assumption, we can calculate a new V out, right? V out, guess one, is going to be 6 VD, which is 6 times our thermal voltage times the natural log of ID divided by IS. That's nothing more than this equation rearranged to solve for our diode voltage. So we're using our exponential diode model. And if we plug in our numbers here, we get 4.873 volts as our output voltage. Okay. Now this is a first approximation. What we're going to do now is we're going to use that new output voltage and rework these same steps until our solution converges, meaning that we see only small variations between subsequent iterations. So for instance, if we see that the output voltage changes by only say 1 millivolt or something like that, that's probably a pretty good metric for saying that we figured out how this thing behaves. So our second guess, we're going to have IX2 is equal to 9.5 volts minus 4.873 volts, which was our new output voltage, divided by 42 ohms, is equal to 110.170 milliamps, giving us a diode current, ID2, of 30.170 milliamps. And from this, V out 2 is going to be 6 VT times the natural log of ID2 over IS. Plugging in those numbers, I get 4.864 volts. And so we've had a change of roughly 9 millivolts. So we probably need to do at least 1 or 2 more iterations. So for our third guess, nine and a half volts minus 4.864 volts divided by 42 ohms is equal to 110.378 milliamps, giving us a diode current of 30.378 milliamps. And this gives us then V out for guess 3 is again 6 VT times the natural log of ID3 over IS, 4.865, volts. So that's a change of 1 millivolt, good enough for me. So 3 iterations was enough to do it. Our change in voltage is then simply 4.865 minus 4.8, or approximately 65 millivolts. So if we bump up our power supply voltage by half a volt, we see that our output voltage only changes by 65 millivolts. So this is still doing a pretty good job of being a voltage regulator. It's still somewhere around, right? Now, what we're going to talk about today is more of this perturbation theory, measuring small changes in an easier way to do it. Because while this isn't particularly difficult, if we had changed, say, we wanted to know what the change was if we had put our output voltage, or excuse me, changed our input from 9 to 10 volts, a 1 volt change. When I did it, it took me 7 iterations to settle, which is why I backed it down to 9.5 for you guys, because I didn't want to spend over half the class doing one stupid problem to illustrate a point, okay? All right, so with that in mind, we are going to develop what's called the small signal diode model, all right? So the small signal diode model is used to see how our diode current ID changes with small changes in VD and vice versa. It can be used both ways. So we draw a picture here to kind of illustrate what we're going to be talking about. That's probably more than I need. All right, so here is our diode current. Here is our diode voltage axis. And here is our diode current as a function of diode voltage, our exponential model. Nothing wild or crazy there. So I'm going to call this point VD1 and this point VD2, and there is a corresponding ID1 and ID2. So when we look at small variations in our diode voltage, so we're just looking at a very small part of our curve here, we can approximate this with a linear relationship, meaning instead of saying it exponentially decays there, if delta VD is approximately equal to VT, then I can approximate this relationship with a straight line. So it's just effectively a tangent line like so. That's only valid around this operating point, or what's more commonly called quiescent point, okay? So under these constraints, let's say that ID1 is IS times the exponential of VD1 divided by VT. We could see then that ID2 is simply IS times the exponential of VD1 plus delta VD, our change, divided by our thermal voltage. We can split our exponential function up into two exponential functions. And this gives us ID1 multiplied by the exponential of delta VD over VT. When delta VD is approximately equal to or smaller than VT, we can use, I believe it's a Taylor series expansion relationship that says the exponential of x is equal to 1 plus x for x less than 1. So using this Taylor series expansion, this is us trying to linearize this relationship. From this, we get ID2 is equal to ID1 times 1 plus delta VD over VT. Which gives us ID1 plus ID1 delta VD over VT. And from this, we can see that the change in the diode current, delta ID, is simply delta VD divided by VT multiplied by ID1. Since delta VD causes a change, delta ID, in our diode current, the diode is actually acting like a resistor. So we have a simple linear relationship here, right? Where we have I is equal to V times some proportional quantity, which is exactly what our resistor behavior gives us. So we are going to define RD is our dynamic resistance. It's called the dynamic resistance because it changes based on where we are on our exponential curve. And it will be defined simply as VT divided by ID. So at our operating point, our dynamic resistance is simply the thermal voltage divided by the diode current of our initial set here. So for our small signals, model, then we go from a diode to this resistance RD. Now this is only applicable for the small signal portion. And so let me explain what I mean by that, all right? If we went into this circuit here, our approach would be, we would analyze the circuit using the constant voltage diode model, just like we did for parts A, and we technically wouldn't even need part B anymore. And then we would turn off all of our large signal bits, which means we zero out all of our DC voltage sources. and DC current sources, and then we only apply the small signal. So it's almost like using superposition. In fact, it is exactly using superposition, but the reason that I'm hesitant to call it that is because realistically, you shouldn't be able to use superposition on a diode circuit because diodes are inherently nonlinear and superposition requires linearity. But we've linearized the large signal portion by using the constant voltage diode model. And we've linearized the small signal portion by using the small signal diode model. So when we put those two things together, we should be okay to do something like that. So let's take our circuit. That we have there. For our small signal model, what was our change delta V? So we went from 9 volts to what? 9.5. So our delta V is 0.5 volts. I'm going to be lazy and just write a 6 next to one diode, which is going to be my shorthand for 6 diodes in series because I don't want to draw anymore. This is going to be our change in delta V. Oh, I forgot my resistor. 2 ohms, like so. Okay. I am not including my cell phone in this model because the cell phone drew a constant current of 80 milliamps, right? So since it doesn't change, it's the DC portion, not the change. So it should not show up in the small signal model. So based on this simple circuit, my dynamic, so I guess, my dynamic resistance RD in this case is going to be, let's see, VT 26 millivolts divided by my large scale diode current, which was 20 milliamps. Uh, 26 over 20 is 1.3 millivolts per milliamperes, gives us a unit of ohms. And so I'm going to replace this guy, my diodes, with 6 1.3 ohm resistors in series. Six times 1.3, 7.8 ohms. And so it should be pretty easy to see now that my change in V out is going to be 0.5 volts times 7.8 ohms divided by 42 plus 7.8 ohms, just using good old voltage division. Sorry, no, 0. I put plus, not multiply. That's why my number was weird. $78.313 millivolts. Now, this value and this value are not the same. right? But they're close enough. So this is just a way for us to do an approximation without having to do multiple iterations to get a result that's effectively good enough to see how this thing. So that's how we employ our small signal diode model. This is called the biasing approach. So to be clear, step one, we separate the input into large and small signal components where large signal is DC and small signal is used for changes or the AC. Find the bias point. Using large signal, CVM, constant voltage drop model, or exponential as is necessary. So depending on the information that we're given, we need to make sure that we ignore small signal AC terms when we do this bias analysis. Step three, after determining the bias point, calculate changes using the small signal model. And then step four, combine the results. So let's look at another problem. And we'll go through this procedure all in one pass, instead of breaking it up and deriving something in the middle of it. All right. So let's say that I have the following circuit. So we have a current source that has both a DC and an AC component. So it's 2.5 amps DC, and then a 2.5 milliamp in amplitude cosine signal put on top of it. And our goal is to figure out what this output voltage is going to be in this diode circuit. okay? So step one says we need to split this guy into two separate models, a large signal model and a small signal model. Sorry, I need to give us two more pieces of information before we move along here. Let's say that VT is 26 millivolts and IS is 2.4 nanoamperes. All right, so based on the information provided, let's start here. Is our small signal, or excuse me, our large signal model going to use the exponential model for the diode or the constant voltage drop model? So if I don't tell you what VD on is, it's the exponential model. If I do tell you what VD on is, it's the constant voltage drop model. That's how you know which one to use. Okay? Just to be very clear about this, your homework, your test, blah, blah, blah. If you're given VD on, use it. If not, use the exponential, which is, in my opinion, slightly harder to use. So for our large signal model, let's do this over here. We are going to have 2.5 amps our 30 ohm resistor, this is going to be our diode current ID, this is going to be our diode voltage VD, and let's see, we're going to have 15 ohms over here. And here is V out. So this is our large signal. So we can express V out in two different ways. All right. So the first way, I could say that V out, the voltage drop over my 15 ohm resistor, is simply the current flowing through my 15 ohm resistor multiplied by the 15 ohms, right? So we're going to have 15 ohms multiplied by, now how am I going to express the current flowing through my 15 ohm resistors in terms of my diode current? Let's start there. Anybody have any thoughts? That's it? Yeah, it's that easy. 2.5 minus ID, just using Kirchhoff's current law here. Our other relationship for V out is going to come from this middle branch, right? So V out would be the voltage drop over the 30 ohm resistor, which is just 30 times ID plus our voltage here, VD. (30 ohms times ID plus VD, where VD is VT natural log of ID over IS. This is our other substitution that we can make, so we're using the exponential model explicitly here and rearranging it so that we have two representations of V out with only a single unknown variable, ID, which should allow us to calculate ID And then once we know that, we can get V out pretty easily, right? Okay, so we put these two guys together. So we have 15 ohms times 2.5 amps minus ID is equal to 30 ohms times ID plus BT, which we know, natural log of ID over IS, which we also know. Now, we need to solve ID. And there are two approaches that we can go about this. One is iterative and annoying, and the other is using a solver on our calculator. So why I say that is the numeric solver on our calculators, the one equation, one unknown solver, actually does solve this type of equation using an iterative process. So either we can do it, which is very time consuming, or we can allow our calculator to do it. So let's take a couple of minutes here and use our one equation, one unknown solver to take care of this. So for folks with a TI, if you hit the second sine function, that's your numerical solver. For folks with a Casio, there's a button on your calculator that literally says solve. That sets up your solver. So let's see, I have 15 times 2.5 minus x is equal to 30x plus 0.026 times the natural log of x over IS. Where did I write that down? 2.4 nanoamps. 2.4 times 10 to the minus 9. We're going to put in a guess value. I'm going to make a stab in the dark and say it's 1 amp. So in your, or at least in the TI calculator doing the one equation, one unknown solver, you have to put in a guess value. If you put in a guess value that's wildly outside the range, it might tell you something like you have a domain error. So start off with something, I don't know, small. Alrighty, so I get 821.979 milliamps. Anybody else get something similar? All right, Jack's nodding his head yes, he's a smart fella, so I'm going to assume we got it right. Cameron, what's up? 2.4. Sorry. 10 to the minus 9. Pico's 10 to the minus 12, femto's 10 to the minus 15, atto's 10 to the minus 18. Haven't had to deal with a number smaller than that, so I don't know those prefixes past that. All right. So let's look at our small signal model now. Oh, actually, we have not yet calculated V out, so that would probably be of use. So using this, V out is 15 ohms times 2.5 amps minus this. .170 volts is what I got. So now let's take a look at our small signal model. Or let me know when I can move along. Actually, that would be better because it's going to require a new page, and so you won't be able to see what I did here. Everybody groovy? All right. So our small signal model means that we're going to have the AC portion of our input, 2.5 cosine omega t milliamps. Here's our 30 ohm resistor. Here is the dynamic resistance RD of the diode. And then here is the 15 ohm resistor. Here is little V out as a function of time. So the first thing that we need to do in order to solve this thing is to determine what our dynamic resistance is. So if you recall, capital ID, our DC biasing point for our diode, gave us a current of 821 point, how did I? 979, thank you. So from this, RD is 26 millivolts divided by this value, $31.630 milliohms. So V out is going to be our current, 2.5 cosine omega t milliamps times the total resistance seen by the current source. I'm doing it the lazy way, so just going to use Ohm's law here. So that is going to be 30.031630 ohms. So that's 30 in series with RD multiplied by 15 ohms divided by 30.031630 ohms plus 15 ohms. No, calculator. So this is going to look like 25.009 cosine omega t millivolts. And our final result then would be to add these two parts together. So our total output is 25.170 volts plus 25.009 cosine omega t millivolts. All right. So fairly straightforward. Hopefully everybody's catching what I'm throwing, because I can absolutely guarantee you something like this is going to be in your test. Okay. So I think that catches us up to where Dr. Batari and his class is. So we got two options. I can start talking about diode applications. So we can talk about half wave rectifiers in a bit more detail, full wave rectifiers, voltage regulators, all that kind of stuff. Start talking about that today, or we can knock off, don't know why that popped up, 20 minutes early. Which one do you choose? Somebody be decisive. David, what did you say? Option that 20 minutes early? All right, 20 minutes early it is. All right, I'll see you guys on Wednesday then. Yeah, most of the homework material, and I don't know why this is set up as like, I looked at the old test. Oh, I didn't send out a roll sheet. Let me do that real quick. I looked at the old test, the old multiple choice test that I think are quite terrible. And the web work, in my opinion, was not very representative of what would be on the exam. And so to rectify that situation, I'm going to be creating a study guide with example problems with the answers so that you guys can work through those that would be significantly more representative of what you should expect to see on the test, so that you don't walk in blind. We've taught you all of this, you've done web work on it, and then, oh, by the way, the test is just random other crap that I mentioned. No, that's wildly unfair in my opinion. So I'm going to be working on a study guide over the next couple of days to give you guys for the test that should make the exam when you get back from the break less terrifying. So, yeah. Yeah, no, I looked at the test and I was like, none of these are hard, but also none of these are what was assigned as homework. And that doesn't seem fair to test you on something we haven't actually asked you to do. So at a minimum, I'm going to give you an opportunity to see what that kind of stuff is.